So our next speaker is Eleni Chatzi.
Thank you very much. So it will be a bit of a change of landscape for my talk, since it is more rooted on the engineering aspects and the inclusion of physics when trying to use models that learn or engage with data. My name is Eleni Chatzi. I'm chair of structural mechanics and monitoring at ETH Zurich, and I'll show you a bit of how we try to fuse physics with learned models for the purpose of digital twinning and monitoring, which is the application at the core of our research. So I would like to first introduce the problem of structural health monitoring, which essentially relies on the perspective of viewing physical assets as cyber-physical systems, in the sense that you initiate from a physical asset on which we can extract information by means of sensing, which nowadays we can actually extract through various types of sensors serving different types of properties, and which come at different precisions and costs that are even deployable on large-scale civil engineering structures, which is a lot of the domain of the activities that I will be overviewing, and which can be used to understand and produce indicators on the condition of a system as is, meaning as it is currently operating, which is more of the task of diagnosis, as well as predicting the behavior and performance of the system in the future, which is the prognostic task. Now, the key to deriving these indicators in a way that is meaningful, we at least advocate in the group, is to use models that are rooted on principles of engineering, on principles of mechanics and dynamics, or first principles in general for understanding the translation of the raw data into meaningful information about system condition and performance. And as a last layer of this, let's call it SHM chain, what we would like to do is to extend this kind of performance from the individual system to the level of a fleet or a population of assets. As you can imagine, this could be the roadway network comprising different types of engineered systems, such as tunnels, bridges, or even the road pavements themselves, or a wind farm, which is a population of individual turbines, or even different types of industrial components that are actually comprised of individual elements that are operating and whose performance is critical to assess. So this talk is going to build on the aspect of modeling, and in order to do this, I would like to actually start from how you can develop models purely on the basis of utilizing data. And again, to place some context in what I will be explaining, I will first overview a few types of data sources that we are dealing with as part of our group at ETH Zurich. So these kinds of data can come from diverse types of systems. A first option for us is to use what is called the mobile sensing approach, which is the deployment of sensors on vehicles, either train or regular vehicles that are traversing different types of infrastructure, and where you're able to derive information on the condition not only of the vehicle itself, but also of the system that it is actually traversing. We're also working very extensively with wind turbine assets, with wind energy assets, including wind turbines, onshore and offshore. And here you see a wind turbine that we own as part of the group at ETH Zurich, and which we use as a living lab for producing different types of scenarios and trying different types of sensing technologies. We also work with traditional civil engineering infrastructure, which is more along the lines of what you see here as different types of bridges and building structures, and of course with industrial components or automotive components as well, which we both test and try to model. So first of all, in deriving a model, perhaps this audience doesn't require a motivation, but as you know, you can nowadays use these types of dense sensing sources to produce models of the system. And a good example for us is what we try to do for wind farms, where you see interaction effects such as the wake effect that you see here play a major role, but where data is actually quite dense. So for these kinds of farms, we have information from all of these individual turbines. They come in the form of what is called SCADA data, which is information on different properties such as the wind velocity and direction at the level of each individual farm. And we can actually use and query this data to produce machine learning-based models of how the interactions within the farm would look, what these interactions would look like, which is, of course, a purely data-driven model, and it can give us a prediction of the flow of the wind within the farm just on the basis of single information from a meteorological mast, basically the condition at the point, the weather conditions at the point of your farm. So this is a generative model. It's also stochastic because it can give us the probability of having these kinds of quantities of interest. It can even go all the way to giving you engineering quantities of interest, such as damage equivalent loads, which is what the engineers would use to understand the remaining useful life of these wind turbines or the reliability of the system. But, of course, it relies on the power of data. So what you see here, or the predictive capability of what you see here, tremendously relies on what is the data that it has seen, and it is not easy to go beyond that. So the caveat of using these kinds of methods, which is why we claim that data is not enough, is that they suffer from what probably you already know as the drawbacks of lacking interpretability, because the learned model is not a construct that you can necessarily understand and then reuse in a way that makes sense in unseen environments. It also lacks explainability, since the physics connotation is absolutely missing, and it cannot very easily generalize beyond what I showed you before, which was the possibility to predict for a set of data that has been used during training, at least the range of conditions that has been used during training. And this is not so well aligned with the engineering task, which is actually a forecasting task. It is a design task. In a way, if you think of it as an analog, we're discussing the situation that resembles this Chinese proverb, where you have blind men trying to feel very locally some sort of asset, in this case an elephant, and understanding different types of truths or realities that are not really representing what is the actual case. So in this talk, I would like to show how you can actually bring physics computation as an inductive bias that is positive for influencing the predictions of your system and trying to go beyond the caveats that were explained before. So engineering will, for us, or the intuition of an engineer will, for us here, serve for building more generalizable and more robust models. So in a sense, we're trying to go from these purely data-driven representations that are, of course, known to work within some constraints. They're even known to excel to what concerns tasks such as diagnostics, for example, and to move to the task of prognosis or understanding how the system will perform, which relies on the exploitation of physics-based representations. So in a sense, we're trying to fuse physics and data in a hybrid construct, which is also known as a hybrid model, for fashioning a twin of the asset that we're actually monitoring, which is both cognitive, understanding how the condition is at the present point in time, and predictive, understanding how we can forecast for different types of tasks, including improving design, possibly even achieving control. And these types of different tasks require that the fusion of the data and the physics is also done in a way that is affordable, which means that our computational models have to be reliable, but also computing in an adequate fashion. This is the overview of the task, where you have an asset, which is actually monitored, which operates with different types of properties, possibly beyond the linear time invariant behavior, which is usually easy to capture and model. It operates under varying environments, different types of operational conditions, under distributed loadings and excitations that are very hard to quantify and usually not possible to measure. And where, of course, as engineers, we may have some sort of intuition on the model describing the system, but the hard task is to align and merge this kind of model with data in a performative manner. In some of the tasks, and for many of our applications, especially for digital twinning, we would like to be able to do this in real time as the data is attained. Although this is not always desirable or a hard constraint, it would be nice to have a fusion that is able to operate on that level. So if you would like to describe the task, in a sense, we're trying to achieve everything everywhere all at once. And this is how it would work. If you have a structural system for which you have sensors in some limited positions of the system, and the system operates typically under unknown input loads, we have, as engineers, an a priori model of the system that can give you an idea of how this can behave, but usually, especially for existing structures such as bridges, this kind of model is not well defined, so it has unknown or uncertain parameters. And what we would like to do is to predict the behavior of the system in its full field, so visibly in every location of this system, even in locations that are not measured, which is why you cannot really escape with black box models, because you need to predict physical quantities that are not actually directly being observed. So we would like to have a specification of everything in the system, which is also known as the task of virtual sensing. And we would like to achieve this under the everywhere, so very densely in our system, under the premises of uncertainty, nonlinear or non-stationary behavior for dynamical systems, observations that are limited and are suffering by noise corruption due to the limitations of our sensors, but also large dimensionality of the actual large-scale systems that we're observing, and we would like to possibly do this in real time, so all at once. And I'm going to show you our approach to achieving something like this. And I would start from where we typically start from as engineers, either civil or mechanical engineers, which is models of computational mechanics. Now, out of curiosity, I know this is a slightly different thing, but I want to check how many of you have studied a course on mechanics. Great, so many of you have, which means that I can at least exploit this as the basis. And so in my group, we develop different models that try to accurately capture mechanics for different types of systems, usually solid mechanics. So we have models for accurately capturing fracture phenomena, nonlinear phenomena such as plasticity, large deformations, and even substructuring for large assembly systems. But all of these models simply do not make the cut. So they're not fast enough to merge with data for the kind of task that I described earlier. So the very first thing we have to do is to actually reduce these types of models to the point where the computation makes sense and even is achieved in fragments of the second, which is really what we would need for our compute. One way to do this is to start by actually using the original, what we would call full-order structural mechanics or mechanics models, and to produce several realizations, computations of these models. What you can do next is to take the time history data from such models and pass them through a feature extractor, such as an autoencoder, for example, but additionally, an integrator that is able to follow the dynamics, which for us would be a type of recurrent neural network or an LSTM. The benefit in this being that you can actually solve your dynamics equations in the lower dimensional space, which is the feature space of the autoencoder, but at any point in time, you can actually return back through the decoding step into your original physical system, which is the full-order finite element model in our case, for example, where the physical properties actually lie and where the monitored properties also exist. So quantities such as accelerations or strains will be linked to this full-order space. Now, in our case, we use this to make the analogy of reduction to what we call the nonlinear normal modes of dynamics in the work of Petros, which is also very closely related for uncovering LED, learning efficient or equivalent dynamics. You can see something similar for more generalized systems. But just to show you the use case for us, you see that what we tried to do experimentally was to show that indeed we derive these independent representations by using specific versions of the autoencoder. So for example, by using a variational autoencoder, you're encouraging a spherical Gaussian latent space, which means that the components are independent and are easy to separate in the spectral domain, which is a particular interest for us for manufacturing a model that is efficient. And then we use this kind of logic for an actual problem, which is to approximate the response of wind turbine monopile structures. This was a problem that was given to us by our collaborators in Siemens Gamesa. And the problem here is actually a nonlinear problem, which is induced due to the soil structure interaction. We're trying to capture the nonlinear dynamics that is generated from these actual systems by using or fitting a model that computes only in fragments of seconds instead of the several hours that this compute would require for the actual engineering task. Now, in what I described so far, we have a model, a construct that produces a model that can compute fast. You need to devote some time in training, but for us, it's more of the actual time during testing that would matter in this kind of application. The drawback is that I have not yet shown how to condition this kind of model for different parameters so that it is really a generalizable kind of approach. So next, I would like to show you an approach that we have or that we typically adopt for producing reduced order models of dynamical systems that are fast to compute but also conditioned on different types of parameters that are underlying our problem. And to do this, we have actually constructed, again, more of a structural engineering perspective, but a benchmark structure that is a structure of several degrees of freedom. It's a dynamical system that exhibits nonlinear hysteretic response. and is actually described by a set of multiple parameters, including the configuration of this structural system itself, which are basically the stiffness properties of this shear frame, but also the properties of the input to the frame, the loading of the frame, which for us is an earthquake type of load that is characterized by its spectral and temporal properties over time. So we can even break down an earthquake into a set of parameters, and we would like to be able to feed these parameters into our configuration, and we would like our reduced order model to spit out very fast the entire time history simulation of this nonlinear system for different types of these parameters. So to do this, we're actually here indeed capitalizing on the physics of the problem, and for us, in these kinds of problems, the physics is usually an ordinary differential, it's a differential equation of second order, which is nonlinear, and which is conditioned on the parameters that I explained before are governing the problem. And what we can do is to initiate from this original simulator, which usually could be a finite element model of a large number of degrees of freedom. We produce, again, multiple simulations from this reference model, and we use a projection type of approach. In this case, it's a Galerkin projection basis that we generate on the basis of a singular value decomposition, more or less. But what this helps us do is to take the original nonlinear equation and transform it into a far reduced number of degrees of freedom. The system and the problem still remains nonlinear, but we're able to solve it more efficiently at some sort of compromise of the accuracy. Now, the compromise of this accuracy depends on how you produce this reduced order basis. And there's many ways to do this. You can basically follow a clustering in the parameter space and produce these reduced basis vectors at different sections of the parameter space, and then use a nearest neighbor approach to solve the problem. However, for us, this was not very efficient. We prefer to have a functional dependence of how to produce these reduced models on the basis of the input parameters, and this is what we did by bringing back this logic of the use of a conditional variational autoencoder. So you have the parameters of your problem, W, you have some sort of coefficients that can generate these reduced bases, and we can actually condition our problem to generate these kinds of coefficients on the basis of the selection of the problem parameters. What is the configuration of that structure, of that system, and what are the properties of the input? So if we do that, we can then generate the full time histories of the problem with different levels of accuracy depending on where you are in the parameter space, but in all cases, with admissible accuracy for our purposes. And so now we have a model that computes fast, but additionally, since we used a generative model that is of stochastic nature, we can also have an estimate of the confidence that we have in this estimation, in this time history estimation. So we have the confidence intervals which somehow quantify the level of precision that we expect from our reduced order model, because you have to remember that any kind of reduction always means also a compromise of the precision of the system. So this was for the small intro that included some principles of mechanics, which is how you can make these models compute fast. And now I would like to go to the core part of the talk, which is the combination of these models with data. Now, what we advocate as part of our group is that there are different ways in which you can figure out this balance, and will always depend on the task that you have at hand. Depending on the level of physics that you claim to know, you can find yourself navigating somewhere here on the upper left corner of this graph, as opposed to the cases where you cannot very heavily rely on physics, but you actually have data at hand, which would take you more to the black box corner of this diagram. But everything you have in between are different levels of actually weighing the physics and the actual learning from the data, which we position in this kind of a spectrum in one of our recent position papers. So here I'll show you some of the options that we describe in that spectrum, and I will start first from what is closest to a white box approach. So the case where you claim to know a lot about the physics that describes the problem. Okay, so let's start from that. In such a case, you can assume that you have a model of the system similar to the one that I described earlier, which can be a reduced order model so that it is efficient, which describes, in our case, the dynamics of the problem, which you see here in this kind of first process equation. And then you also have information from data in sparse locations. You cannot have this everywhere from the system, that gives you the connection between the model and what is actually the reality. So you have a model proposition, possibly a reduced order model, the data that is extracted from the system, but also uncertainty, which we know is there, first of all, due to the approximation. that we introduce by using a simplified model, but also due to the sensing aspect itself, which comes with some sort of corruption in terms of the quantities that we can derive from the system. Now, a way to navigate through this landscape and to somehow merge this information, the first equation that was physics and dynamics, and the second equation that was the data and the measurements, is to use the Bayesian principle. And we do this in this case by applying the Bayesian principle at every time step in what is known as a Bayesian filtering approach, which many of you have already experienced through the use of Kalman filters, for example, as part of some of your studies. In this case, because we have nonlinear systems, we resort to the use of particle-based methods. So we assume that the state of our problem, which is the dynamics, is represented by a finite set of particles that tries to capture or to reflect this state as a probabilistic distribution. And since we have equations, we can use the first equation, which is the equation of the dynamics, and propagate these particles to understand what is the position or the property, the dynamic properties of our system at the next point in time, because this is what the dynamics equation can do. It takes you from time tk minus 1 to time tk. Now, what we're missing so far is the contribution of data, and this comes at the next step. We can take this prior estimation. We can use our model to understand what it would predict with its current configuration in terms of the derived measurements, and we can look at the discrepancy between the measurements and the prediction to derive an improved posterior estimation of the state of our system. So we can basically weigh the dynamics by using both the contribution of the physics laws and the data, and we do this using the Bayesian principle powered by the physics that is represented in these reduced order models. Now, the problem is, of course, a bit more complicated than this, and it depends on the task that you wish to achieve. So as part of our group, we have developed different schemes for state estimation, which means the response of the system at every location of the system, even beyond the locations where you measure. Joint state and parameter estimation, which means that while estimating the response, you can also estimate the parametric configuration of the system. Input state estimation, which means you can also derive the unknown loads that are acting on the system under different conditions, or you can try to do everything again all at once, which is this input state parameter estimation problem, which of course can be ill-posed, but depending on the observations you have, and if certain conditions such as invertibility, observability, and identifiability are satisfied, you can also actually achieve such a task. And so you can find these kinds of tools. We have developed them and bundled them in a tutorial, which is described by both a paper, but also the corresponding codes that can be used to solve all of these different tasks of varying complexity for dynamical systems where you have some sort of model. Doesn't have to be structural mechanics. It can also have, come from other principles that govern the physics of your problem and data that are derived from sensors. Now, I would like to show you a case study that is a bit more elevated, because our previous benchmark was just there to show you the principle and the conditioning, but the problem starts becoming interesting when you have a higher complexity system. So here I'm showing you an application from one of our problems in aerospace, where we're trying to see if we can simulate this kind of aircraft structure, specifically a fuselage panel, which is a thin shell structure, on which we assume that we have some limited amount of point sensors that derive properties such as acceleration or strain, in this case acceleration. And we would like to see if we can produce such a hybrid computation scheme that allows us to do digital twinning tasks, so basically to understand and predict the time history response of the system in real time in unmeasured locations, but also damage inference tasks. So assuming that there is a defect or multiple defects in the system, we would like to see if we're able to infer their location and, let's say, positioning and extent. Now, to do this, because this problem is more complex, we need to use a stronger computational mechanics approach. We here use our favorite approach, which is an extended finite element method, which, as mentioned before, cannot compute fast enough. We would need to reduce it, as I explained earlier, and then fuse it with data using this Bayesian principle that I mentioned earlier, so that we can do the prediction and the inference in real time. Now, the reduction method is similar to what I explained before. There are a few intricacies that I think are beyond the scope of this talk, so I will not very deeply explain. But the fact that here are parameters, which is basically the position and orientation of the crack, induce a non-smooth problem, makes the solution of the problem also non-trivial. It means that we have to figure out a way to extract these bases in a way that is efficient. Typically, if you have ever solved the fracture mechanics problem, you would know that the tendency is to remesh and define new nodes when you have a cracked surface. Here, for us, this would not work because it means we would have a new number of nodes and we cannot actually reduce our model. So we use mesh morphing, which is essentially a trick so that we have a fixed amount of nodes, but we're able to represent different positionings and configurations of the crack in our geometry, even if it is actually a curved structure. And then, using the projection-based approach, we can build this parametric or parameterized reduced order model that computes the vibration of this kind of surface when it is cracked in real time, so actually faster than this video is rendered in this case. If we have this reduced order model, we can then place it as the main computational or physics engine inside the Bayesian filtering approach that I explained before. This is actually a problem that's very close to our daily business in the sense that also here we do not know the input load to this system. We cannot really claim that we have an accurate measurement of the pressure or a full measurement of the input field to this aircraft, so we assume that the load is unknown. We have different ways of tackling the evolution of that unknown parameter, but we can basically place it in a type of filter such as the one I explained before. And here we can achieve this kind of joint state parameter and input estimation task, which means that by using this reduced order model and placing it inside of the filter and using the four sensor information that we had before, we can first of all achieve the inference task, so the damage inference, meaning that we can understand where the location, what are the characteristics of the cracks, if any, are actually present on the location on the surface that we're exploring. And quite importantly for us, we can also predict the response of the system in these unmeasured locations, essentially in the full field, since you have an engineering model. And we can do this in real time for facilitating other types of tasks, possibly tasks of control, for instance, that could be of relevance. The reason why this is possible is because we now have a reduced order model that computes at fragments of a second, as opposed to the original computation, which would be much lengthier, even if we were to use an accelerated and improved model. Now, of course, this was just simulation, and now it makes more sense, or it is more convincing, to show you an application where this has been applied. So here I'm showing you an application of this kind of a logic in collaboration with Siemens Industry Software, who are our partners. Here, Silvia Vettori, who is a former PhD student of our group, has actually implemented this approach for simulating or digital twinning a wind turbine blade structure. You see the blade here mounted inside the lab facility at DTU, where the collaborators of this program were. And what Silvia did was to use an augmented Kalman filter that was using a structural mechanics model of the blade that was reduced and fused it with the sensing information along this blade that comes from sensors of different properties, such as strain gauges and accelerometers. And then, through her computation, she's able to deliver a predictive tool that can give us actually the stress distribution all through this blade in real time, transferred to the tablet here of engineers that can then use it for all sorts of downstream tasks that have to do with condition assessment, either through derivation of indicators of the performance of the system by using the estimated stresses, or even for forecasting further aspects that have to do with the resilience of the system, such as what is the remaining useful life, or what would be the robustness of the system under increased loads. As part of the group, we now have two spin-offs that are taking these ideas and are implementing them into practice. So RTDT is using these ideas for wind turbine systems, and IRMOS Technologies are implementing these ideas for the monitoring of civil infrastructural assets at the moment, always capitalizing on the fusion of data with these physics-based models. Now, I remind you that up to this point, I was pretty high up on the left corner of that graph, where I assume I know a lot about the physics. Basically, what I was saying is that the model that we have at hand is enough to describe the phenomena that we're observing. It's so good that there's actually very little discrepancy between what we measure and what we can actually produce by means of a model. But in many situations, this is not the case, especially for systems that are more more complex in nature. In this case, we cannot claim that we know all of the physics that can adequately describe the problem, and oftentimes this is the case for nonlinearities, but also for phenomena that have to do with damping and dissipation of energy that are not very well described or understood. So in that case, we have what we would call a model form uncertainty. And in that case, you have to start moving lower down the spectrum from towards, let's say, a heavier exploitation of data. Now, we have assembled some of these options that you see also mentioned there in the label, again, in a recent paper, which is complete with the codes that produce these kinds of physics-enhanced, as we would call them, models. And I will show you here just some of the versions that we have been toying with. Before I start explaining that, let me explain what would be the absolute black box version, where you try to model a dynamical system with this Bayesian logic, so at every point in time, but without claiming that you know anything about the dynamics. So what you could use in this case for achieving such a task is to use a temporal variational autoencoder, which is also known as a deep Markov model. In this case, you can actually derive the dynamics of the system, which is the transition function, and the reliance of the observations that you have on that latent dynamics, which is no longer a physical variable, by deriving an appropriate emission function and an appropriate inference model. All of these can be, in this case, not preset, as I showed before for the Bayesian filtering, but they're inferable. So you can figure out what this F and what this G is, what is the model of the dynamics, and what is the model for our observations, just by using data. The drawback is that this Z, the latent variable, does no longer live in the physical space of your system. It's a latent variable that does not have physical connotation and is not necessarily explainable. So also your predictions are only limited to what you can explain, which is really what are the locations that you observe. So this kind of model is not so helpful, but of course it's very good when you don't have any idea about how the system operates. What we would like to do is to improve its generalization ability by bringing in these concepts that we showed before from the other edge of the spectrum. We're trying to compromise this idea of physics and data, knowing that the physics we have at the moment is not perfect, is not going to perfectly capture our problem. Now, there are different ways actually for doing this in what we would call the umbrella of families under the title Physics-Enhanced Machine Learning Schemes. With our group in Singapore, at the Singapore ETH Center, we have been developing different types of schemes that can then be clustered in subcategories, let's call them, according to the way in which you choose to fuse physics into your equations. If you explicitly, for example, use your physics equation to govern the transition or influence the transition model of your system, then this is what we would call a physics-guided scheme. Here, the presence of physics is more strict. It's already embedded as an equation into the workings of your system. If you try to do it by using architectures that are particularly favorable for the dynamics tasks, such as, for example, ordinary differential equations, or systems that use integration schemes that respect Hamiltonian laws, such as symplectic encoders, then we're talking about physics-encoded schemes. Or if you try to do it by loosely including weak formulations of the problem into your loss function, which is more of a loose constraint, then we're discussing physics-informed schemes. So here I'm going to show you some of these variants and how these work for us, starting by the physics-guided scheme, because it is the closest to what I tried to explain before, the concept that you may have a model of the system, but this is not perfect, and you would like to combine this with data so that you can figure out what is left, basically the discrepancy between what you know and what is the real situation. In this case, we can imagine to actually use this, whatever is the physics model of the system that you have, even if it is faulty, even if it is not complete, and you can seed it into the transition model of your system. This is what we will do here. We take the DMM architecture and we fuse this kind of known transition, but we admit that it is not perfect, and therefore we also have in parallel a term that is there to take on the model discrepancy, a term that is to be learned from data. So if you look at the deep Markov model architecture that I showed before that was a black box, what we change here is that in the transition function, we no longer have one, but two tracks, the first of which is fully defined by the physics model, the part of the physics that you claim that you know. We accordingly then modify the derivation of, or the definition of the elbow, and then we're able to discover not only the parameters of these black box or learnable models, but also the parameters that have to do with the problem that, or the model that defines the physics. I'm going to show you a very simple example just to make the point clear. So this is the example of a pendulum, which is a nonlinear oscillator. The full equations for such a simple problem are of nonlinear nature. This is, again, a simple problem that just tries to make a point. But what we will do is we will claim that we do not know the entire physics. We will use a linearized model, which is obviously insufficient or not as complete. And we will use that for predicting the dynamics of this system. And we will try to learn what we do not know by using this logic of the physics-guided deep Markov model. You see here, first of all, the performance on the right of the black box model, because you can achieve this task also by using the DMM. What is the task? We have a set of videos, basically images of this kind of a pendulum structure, which you see here. And this is also the nice thing about these constructs, that you don't have to have a very clearly structured set of data. It can also be abstracted, it can also be in the form of images and videos, as it is here. And you try to see what would be the latent space that is uncovered. And of course, for the DMM, what it can very successfully track is actually the displacement, which is what you feed it, is the observation that you feed through the images. But it cannot give you a state space, a phase space that would make sense, because it's not the task of the black box model to understand the physics here. The fact that we would like the latent space to also comprise the velocity, which is the derivative of that displacement or angle. To the contrary, by using this simplified linearized model, you're actually explicitly seeding these physics. You are requesting the latent space to comprise theta and its derivative, which is what now gives us the chance to derive a latent space here on the left. Let me see if I can do it here. That is actually fully interpretable. Although we're not actually observing the angular velocity, we're able to predict it, which means that we're achieving this kind of virtual sensing that is necessary for us, predicting dynamic quantities that are not directly measured. Now, this was a simple problem, but we actually use this kind of a principle for practical settings. And one of these settings I explained in the beginning for us is drive-by monitoring or onboard monitoring, where we use sensors on vehicles, either on train systems or actual road vehicles, to understand the condition of the substructure. Here we're using sensors that are relatively low cost, such as MEMS technologies. We're extracting indirect indicators of the condition of the substrate, the roads or the bridges that are being traversed, which are reflected in the use of vibrational, or collected via use of vibrational data, typically accelerometers that are mounted on these vehicles, and we're trying to achieve infrastructure assessment. This is a task that we're pursuing both in Switzerland with the Swiss Federal Railways, as well as in Singapore with different partners. And here we're also bringing this kind of a concept. So here we have vehicles of general nature that are instrumented. We cannot claim to know precisely the model of these vehicles, but we know more or less that we can approximate them with some sort of engineering model, and we're using this kind of information as the part of the physics that we adopt for the system, whereas we try to learn the rest of the dynamics of these systems by using sufficient data. And we do that with the purpose of understanding properties of the substrate, for example, the roughness of the traversed infrastructure. So here I'm showing you how this would perform if you were to use this kind of physics-guided model where you mix the two terms, and you see that there is an optimal mixing that would give you the faster convergence and a higher precision. Of course, it's not the task of the user to define this mixing. It's an inferable parameter that is learned by the algorithm, but it shows you that, for example, if you rely more on physics when it is wrong, you can have an off behavior, and the same if you rely too much on data that is maybe imprecise. We're now going to be corroborating this kind of approach on a project we have with India, with the Indian government and the Roads Office, where we will be instrumenting a vehicle for understanding the condition of new highways. This is a collaboration with Kissler, a sensing company based in Switzerland, and our spin-off RTDT. But we're also doing something similar using trains for the Swiss Federal Railways. In this case, using trains to understand the condition of bridge infrastructure systems, which is a more complex task, because also there are interaction aspects between the bridge, so the structure, and the vehicle that are not very easy to model. So again, we have to rely partially on what we claim to know from the physics and what can be learned from these kinds of learnable models. Now, this principle of using biases that are, let's say, positive for the behavior of the system does not have to strictly rely on physics. You can also impose aspects such as structure and dynamics that can also be beneficial. And this is what we did here in the neural extended Kalman filter. Again, we took the black box deep Markov model architecture, and we tried to impose actually the evolution or inference equations that we know apply from nonlinear Bayesian filtering, which was the first case that I showed. There, we have very well formulated frameworks on what should be the update equations on the basis of our nonlinear functions. And so it turns out that if you impose them on the formulation of the inference problem, although it's not straightforward physics, it is structure that is actually beneficial for learning the structural dynamics representations. Again, you would find this kind of a model together with code, completely open, where we show how you can use it as something that is actually a gray box, something between the black box temporal variational autoencoder and the white box extended Kalman filter that uses prescribed physics of the problem. There are several benefits to this. I won't stay too long here. I will just show you how this works on actual applications, which is really the motivation for us. For example, the prediction of the time history response of a building structure under real earthquakes. This comes from real buildings and real records that we have access to, or are open access for researchers to attempt these kinds of simulations. Here as well, it's not very easy to define a very successful model of the system, so we benefit from using these learnable representations. Here in this experiment, we also do this for experimental prediction of blade structures and understanding where damage could occur. Or for the purposes of control, we can do something similar. In this case, I'm showing you what we call the physics-informed neural ODE, which is again a neural ODE construct, which has part of the dynamics regulated by a physics equation. We try to do this for this shear frame structure, which is a building system that we would like to control. And for doing this, we should be able to understand the response of the system in dense locations during operation. So we achieve this, but what is also quite interesting for us, and probably also interesting for other applications, is that the learned part does not really have to stay as a black box either, because you're fitting a function, even if it is a neural network function, and as a next step, it would be possible to apply dictionary methods if you suspect what would be the terms that regulate these dynamics, and fit these kinds of known functions into the black box term. In this way, actually inferring in some form even the physics that is unknown. So we could discover the physics that we're missing by using this kind of an approach, in this case, using sparse regression for understanding what was the recovered term. And then, as we're nearing completion, I would like to show you what is next for us and why we resorted to the development of these kinds of methods. As I mentioned earlier, one idea is to try and extend these kinds of predictions to the level of a system. So for example, for these onboard monitoring systems that we develop, we're now trying to see with actual platforms how the extraction of data with low-cost sensors that we put together from extended infrastructural systems can translate into the assessment or condition indicators for these kinds of systems at large. To begin with, for our project in Singapore, we have actually used this kind of low-cost mix of sensors that are deployed onto a robotic platform, which is this kind of toy robot that you see here. We deployed this kind of sensing solutions, and now we have this robot traversing the shoulders of bridges, collecting information about the dynamics of bridge structures through Singapore, through a pilot collaboration with the Land Transport Authority there. And we do the same with bicycles, where we mount this kind of sensing box, and we use these bicycles to traverse the bicycle network and then derive indicators of the condition of that network, meaning the condition of the pavements, what is the comfort of the user, and then plot it in real time on our platform tool. So we are able, if we have such computing models, to then also deploy them at scale, but the idea is to also use them for supporting decisions. And a way in which you can do that is, again, through a stochastic type of framework that derives these indicators of performance for our subsystem. In this case, I'm showing you an application with the Swiss Federal Railways again. Here we're interested in understanding the condition of the ballast, which is the condition of the substructure, what is essentially under the rails. Usually we're looking into moisture problems, problems that have to do with the regularity of the rails that can actually result into accidents. And in order to derive this information, we use the principle that I showed before. We extract indicators that rely on cheap to collect information. In this case, we're using a fractal value indicator that comes from acceleration recordings of a diagnostic vehicle. We collect these over time, and then we try to build a model that in this case exploits this historical data. In our case, it's a partially observable Markov decision process that tries to advise on the basis of these observations and their effects onto the system, what is the optimal action to take so that the operation and maintenance of these systems is optimized within a planning horizon, typically of several years for these kinds of applications. Now, to solve this problem, there are different ways to formalize it. We have used the POMDP approach, which I show here, but it's also very interesting to formulate it as a reinforcement learning problem where you discover even the environment, again relying on the principles that I showed before, and we're actually using the deep Markov model to discover this environment while placing it in a reinforcement learning setting. The further aspect that we're interested in is learning at, again, the ecosystem level. And here, some of the additional biases that can be exploited are actually also the interconnectivities of the components of the network. And you can very conveniently fuse such information by using graph-based representations. So we're also using graph neural networks, which could contain within them biases of the physics for understanding performance of systems such as wind farms, where the interactions are paramount, and where we would like to generalize, understand the performance of new systems, meaning new farms that are about to be deployed for specific site conditions by learning on previously monitored populations. These graph-based neural network models allow us to have such predictive potential that can also guide the design and optimization of deployment of these systems. So with this, I would like to actually come slowly to my conclusion, which tried to offer you this overview of building digital twin representations that are what we call augmented, in the sense that they comprise various layers, starting from the data itself, which contains a lot of information, but which needs translation and interpretation, which is where the models come in play. But of course, these models have to be efficient, have to be performant, have to be compliant with the requirements of your downstream task. And oftentimes, this has to take into account the expert in the loop, which is the engineer or the operator, for the decision support process, so that you can reach an assessment that is really optimal at the ecosystem or population level. So I would leave you with this slide, and I guess I would also be happy to take any questions. Thank you very much.
Thank you very much. Any questions from the audience?
Eleni, thank you very much for this stimulating talk.
Thank
it
you.
was so stimulating that I need to pretend that I am a second-year undergraduate at NTUA, and I want to ask you the following question.
Yes.
And I suppose there are many undergraduates in this room, this for sure. How about AI-informed physics? In the sense that, can we, to put it to the extreme, actually that was a actual question I was asked in my fluid mechanics course from a second year at the graduate in chemical engineering school. Can we discover Navier-Stokes equations or the pendulum equations by using data?
Yeah, well, this is my point, actually, that depending on the level of physics you claim to know, you can have, this is what we try to do here, right? We know something that is not complete, and we try to complement what we do not know by learning from the data, and even then try to decipher it, like what is the functional form of that thing. You can also have equation discovery purely on the basis of data. This has been shown and it has happened. What the issue is, though, in these cases, that you usually have representations that are not necessarily at the coordinate space that I would be interested in. It's usually at the latent space that is great, of course, describes the dynamics. It's not very easy to translate into the full field, and that's why you see me resorting into the use of this partial physics oftentimes, because it helps me bring the coordinate system in what it is that I observe and monitor, which is particularly actually tied to our downstream task, of course. But if you're interested in inferring latent spaces for dynamical systems of general nature, of course you can also do this purely on the basis of data. The question is, how useful is the model then for these kinds of tasks? I don't know if this covered your question.
Well, partially, yes. No, well, actually, there's a temptation to ask you the following question. In the context of HIAS, the Hellenic Institute of Advanced Studies, how can these great ideas and prospects can be shared with Greek interests? You cooperate with Singapore, of course you work very hard in Switzerland. How about Greece? There are so many things that you touched upon there. That's very tempting for the growth and
this is true. So I also tried to structure my presentation in a way that is motivated by the use cases, because you have to understand in monitoring, we're driven by the problems and questions that arise from the use cases. We cannot have a problem that is purely philosophical in the context that I described. And we are interested in partners everywhere. Actually, in Greece as well, there is a large-scale project now going on involving 250 bridges that are being monitored and where I serve as the scientific advisor. So you will see it soon, probably also featured. This is a collaboration with Kostas Papadimitriou, who's also in the room. So it is something we're pursuing, and if there are chances in Greece, then we're particularly interested in these as well.
A question on dynamical systems. So in particular, whenever you have chaotic dynamical systems, then there is an issue there. And I was wondering, what are your experiences? Do you think artificial intelligence methods, any kind of them, are capable of forecasting chaotic dynamics?
Yeah. So chaotic dynamics is one of the reasons why I think it's very beneficial to actually try and fuse whatever is the physics constant that you know of. I also think it's not very fair to show performances of these learned models under very restrictive and specific environments where they can do well within some range of initial conditions, but of course completely overshoot otherwise. And we know that this can happen, and this is the case. I think that conditioning is very essential there. So if you manage to have conditioning also for these kinds of predictive models in a way that it could feasibly give you these branched solutions, maybe we can have a solution. But still, for me, the solution for managing the problem in a way that meets our expectations, meets what we know should be there, is to fuse that as a bias. If you know that's going to happen, then put it into the aspect of the modeling and the simulation.
So you're saying that if I have a chaotic system and I know that the trajectories are going to diverge...
Exactly, try to
put it in a...
Or try to construct your training set in a way that observes these different manifestations, or if that is not feasible, try to seed in some part of the equation that you know is describing the problem into that, which is what we try to do here.
Okay, thank you.
Hi. You mentioned that you need some form of data, like a lot of data, I guess, for the neural network modeling part of the two-track architecture that I see. I'm wondering how robust these kind of architectures can be in different noises of data, because
this is, of course, something that we look into, because we actually, whenever we construct such a model, we have to do it by also assuming different levels of noise corruption for these data sets. So we always explore that. And of course, as you realize, when you start corrupting it with something that is higher than perhaps realistic, the model may break down. And that's what it should do, in fact. But again, because we're driven by real applications, we can show that this would work for the actual expected levels of noises that we know, at least for sensors, they are very, very well described by specifications. The other aspect of noise is what comes from the insufficiency of the model, so this is something we also toy with. And then we try to always match with the actual observed behavior. there's no, there's no value to these models unless there's validation, which is why you saw me insisting on showing experimental and full-field validation cases.
Other questions?
Yes, over here. Thank you both.
Yeah, sorry. First of all, I would like to thank you about your presentation, and I would like to ask that in the beginning of your presentations, in the slides, you show that you are collaborating with wine firms and wind parks. Wind parks and railways. Are you doing this to solve? I mean, is this collaboration has to do with only collecting data and studying in physical term, or like solving problems maybe these sectors they have also?
No, it's primarily motivated by solving the problems they have. The primary problem being the one of condition assessment, both in terms of what is the condition right now and is there damage right now, which is the most common request, but also predictive tasks. How higher loads can I anticipate in the future, and will my system perform for the next some years? What is the remaining useful life? And this is why we try to deliver these twin representations.
It's possible please to bring an example, if it's okay.
For example, for the wind turbine for the aerospace structure, which I showed, we tried to extract this data and understand where the cracks could be on this system. A very similar problem is there for wind turbine blades, where you try to see if there is damage onto the blade or the tower of the wind turbine, if there is erosion, if there is icing on the blade, which are quite common problems. Then there is the matter of the foundation of these structures, which are very hard to monitor, and so you have to indirectly monitor them. Therefore, you need to have a model that connects the actual measurements on a tower with what you have in the foundation of a monopile or a jacket structure, for example. So these are the types of things you would be interested in from a damage identification and quantification point of view. For remaining useful life assessment, the biggest aspect for our systems is fatigue. And so what you should have there in order to predict fatigue is some sort of model that predicts strain and stress evolution. And so these kinds of mechanics models are necessary there so that you can impose the loads that you expect in the future, and under this condition also calculate the damage equivalent load, let's say, which is the expectancy of the system.
Thanks a lot.
Yes, thank you for the stimulating presentation. Actually, on the specific slide, my first question is, when the problem is of many different time scales and size scales, what kind of data do you need, I mean, qualitatively and quantitatively?
When you say different time scales, what would you have in mind? I can give you an example maybe from our case, but maybe you have something else in mind, that's why I asked.
Yeah, actually my problem is of a different domain. So we have ships sailing at sea, and you have the one scale of the actual time and moving in waves, and another time scale of a propeller rotating, and a wider time scale of fouling developing. So
yeah. I mean, these kinds of reductions have also been shown on kind of multi-physics types of problems, and there are substructuring methods as well that try to take this on. They solve the dynamics that is finer in one scale, and then they try to integrate this with a surrounding medium that is of a coarser scale. So, I mean, things like this are possible. But what I would say is that the benefit of such architectures is that this probably can be taken into account by attributing different features, that maybe you devote different effort to compute at the scale of time that is appropriate for each one, and then you bring them together into something that still describes in a cumulative fashion the problem. For us, graphs are very important for this kind of justification, because there with the flow in wind farms, we have such issues. And there you would see, for example, that we do computation of nodal and edge features at higher sampling rates, whereas global features usually evolve at a different time scale. So we do a conditioning at these, let's say, slower evolving features, but all of them can align in the same construct.
And my second question
sorry, let other people ask questions as well. So one final question.
Thank you very much for a very interesting presentation. My question is also on this slide. First of all, something potentially stupid, and I apologize if I'm not understanding. Is in this case the dynamics ruled by the physics and the neural network additive?
So it is additive. In this case, we assume a simple superposition. It's not necessary. In this specific model, it's a superposition.
Okay. So In this case, you're trying to figure out a closed form approximation to the neural network.
To the learned term, yeah.
Yes. Have you obtained any truly intuitive closed form solutions, or try to obtain some new, like understand some new laws that, because in many cases we get that the neural networks really fit the data and we don't really understand what is happening.
You're right.
Because this is very interesting in the concept of interpretability and explainability, because if you truly obtain some closed form solution that tells you many things, that's very interesting.
Yeah, you're absolutely right. And actually, in this case, the reason why we do obtain a function that makes sense, but the reason is that I sort of biased it. I'm using a dictionary learning type of approach. And the dictionary is formed by basis functions that I think describe the problem. Therefore, what I get is probably what I expect I would get. Of course, you can be very generic with the type of dictionary you assume. In fact, in recent work that I didn't show here with George Kissas, we tried to do something like a vocabulary of material models that is learned by really fusing terms that are more random than what you would typically put in material models, precisely to do what you mentioned, to discover things that are beyond our intuition, but still make sense, because they actually still satisfy semantic constraints, they still satisfy laws that these material constitutive conditions that these laws should satisfy. And so that is the concept there. But it's still building a vocabulary, but now in a more free fashion. And so we try to do it by using grammars in this case, so that we're more flexible. It's not just a fixed selection of what I chose, that is what you see here, but something that's generated in a bit of an arbitrary fashion.
We're out of time. Thank you very much.
Thank you.